It's hard to convey the thrill of scientific discovery in a textbook, and have your mind blown the way that Ernest Rutherford's was when he did his gold foil experiment? Well, you probably had to be there. But we're gonna do our best to bring it home by shooting a bunch of tennis balls at Chris. To preserve the element of surprise, we're not going to tell you much about Rutherford's original experiment right now. But we will tell you that he shot alpha particles through very thin gold foil and tracked where they went by watching for the faint flashes of light the alpha particles made when they hit a screen coated with zinc sulfide. In our model, we've represented the positively charged alpha particles with tennis balls, a single gold atom from Rutherford's gold foil with this foil shield. Like you'd expect, the tennis balls mostly blast straight through the foil. They don't always hit Chris in the same spot, but the foil has very little impact on the ball's trajectory. Except, every once in a while, ow! They bounced off the foil. And that doesn't make much sense. Every tennis ball should have ripped through the foil. Rutherford was similarly confused when some alpha particles started bouncing off of his gold foil. In his own words, "It was quite the most incredible event that had happened in my life. It was almost as incredible as if you fired a 15-inch artillery shell at a piece of tissue paper and it came back and hit you." Ultimately, he made the same conclusion you probably did, that there must be something dense hidden inside of the foil. But that meant he needed to rethink the accepted model of the atom. That model, sometimes referred to as Thomson's plum pudding model, said atoms were little spheres with positive and negative charges scattered throughout. That's why Rutherford assumed that the alpha particles would punch straight through like an artillery shell through tissue paper. But when some of the alpha particles began to bounce back, he concluded that all the positively charged particles were concentrated in a super dense nucleus. A nucleus so dense in mass it could take a blow, and so dense in positive charge that it could repel a positively charged alpha particle. He also concluded that the alpha particles that were blasting straight through the foil were really just blasting into the empty space between the nucleus and the electrons. And since only 1 in 8,000 of those alpha particles was bouncing back, there must have been a lot more empty space in those atoms than the old atomic model suggested. Based on his findings, Rutherford came up with his solar system model of the atom. And although that model has since been replaced, first by Bohr's modified solar system model and later by the quantum model, it was a step in the right direction. That's it for this episode of PS 100. We've got related videos here and in the description below, and be sure to visit science.byu.edu.